that thing. Also do another proof by induction. So we'll do some of this, and at the end we'll have some time to do one more induction proof just for practice. Because we have done a lot of proofs that are, there's only one, technically there's only one method of proof that qualifies as far as I'm concerned as a method. The rest is just a shaking a tree. So you can go counterpositive, you can do contradiction. It's you don't know ahead of time where is it going to work or not. Induction it does qualify as some kind of method. So that you could, if nothing works, you can try by induction. You know where it applies and where you know where it is definitely not going to apply. So in many parts that's entirely not applicable. So anyway, okay, so we have been talking about at the end, so we talked about sets, and we'll get back to that, but remember that one way to, or the only way to actually understand the sets, the relation between them, is actually look at functions between them as well. So one is very much, there's no other way to look at it, is to understand the sizes of sets through functions. Why? Because you only can understand sizes of sets by comparing them to each other. And how do you compare to each other? Number one is through a bijection. Okay, so that's a bijection between them establishes that establishes by definition that these sets have the same size. The presence of a bijection means that they have the same size and the existence. So it doesn't mean that every map function will count, but just presence of one is enough, and we have proven that we did prove that bijections create an equivalence relation on sets, and that is why so all the sets, which are whatever we consider a set, is split into classes, and that are do not overlap, and so then we can justifiably speak of the cardinality of the set in that sense that the two sets have the cardinality whenever there's a bijection between them. Okay, and then furthermore, if we want to go to the next step, is take that comparison to the next level, as we did. So we then speak of whenever the strict inequality might be present. Okay, so less than or equal to set x is smaller than set y when so x, they are sort of first of all not equal to each other. Okay, so there is no bijection between them, because if there is, that they are equivalent, they have the same cardinality. And secondly, there is a one-to-one function from x to y. So this one, it matters which way it goes. Bijections go back and forth. There's a bijection. There's an inverse. So we can take one or the other. That's the equivalence. X, y, y, x, same thing. Here it doesn't matter which one is small, and so we speak of one-to-one function from x to y. Okay, but there is no bijection. So that's what makes two sets, one small, the other. The idea is, it seems like we only brought this up whenever we had to deal with infinite sets, and that is true that that this kind of approach is, I'd say, inevitable. But really it fully applies to finite sets as well, and that is the other thing that we discussed, is what happens when how do you understand numbers in the first place. The numbers are used for counting, and that's how we understand them. It is an establishing a relation between the sheep and the pebbles that you use to count sheep without actually knowing any numbers. Okay, and then you can use the same pebbles to count cows, and then maybe later on you realize that you can count some money or stars in the sky, and that's a number finally a number that used for counting. So integers or natural numbers rather, that's how they appear. So it is a bijection between the different sets. Okay, so then. Well, let's go back slightly to what we talked about here, and that is well, power sets. I guess maybe so that it wouldn't be hanging in the air as much. So this is about finite sets. So you don't really need to bijections to understand the sizes of sets. It is the numbers that you need to understand. You need bijections to understand numbers. That's the way I see it. So so the problem that we chose not to deal with was the number of combinations. The number of combinations. We're looking for the total number of subsets of a set, but in that table over there, this is what we're talking about. In how many ways can you choose, say, 3 out of 4? I'm sorry. Yeah, 3 out of 4. And the answer is 4. Well, but the more interesting number is obviously this one in the middle. So you have 4 elements. In how many ways can you choose 2? And the answer is 6. And there is a formula for that. Okay, so it's a number of combinations. That's the term. So the number of combinations of m out of n. So n m this way, or c in m. And the formula is n, what is it? N factorial divided by n minus m factorial, m factorial. Let me check. Okay, so if I do 4 out of 2, or 2 out of 4 rather, then I'm supposed to have, so 4 factorial divided by 4 minus 2 factorial, 2 factorial, so it's 1, 2, 3, 4, 1, 2, 1, 2. Okay, so 2, yeah, it is 6. Okay, right. So, and then you can that problem that I mentioned, choosing a team of 5 out of a group of 20 potential players. So that's how it's done, and that goes straight into combinatorics and probability, where you got to count things. You know, what is the probability of getting a particular hand in playing poker, say? And under different circumstances, you have to count the number of possible ways it might appear. You need to count the total number of possible, say, hands of 5, say, out of, what is it, 32 cards maybe. So that total will be 32, 5. So a hand of 5 out of 32. That is general, because any card is equally likely to appear in the simplest, at its simplest, and then you choose that. So that will be the denominator, the count of the numbers of total possible outcomes, and then in how many ways can you get the same number of the hand that you want. So such as, I don't know, what hand do you like? Royal flush. So they have to count the number of, in how many ways can you get a royal flush? In how many ways can you get a royal flush? Out of 32, so it is, isn't there, hold on a second, I guess so. Wait a minute. So 32 divided by 4, it is 8 cards, so it's those 4. Is the royal flush is the only way to do royal flush in each suit? Yeah, so okay, well. So if you start at 6, or whatever, that's at 10, rather than at a jack, it doesn't count as a royal flush? What does it count? Is there a name for it?
It's just a flush.
Just a flush?
Straight flush.
Straight flush, okay, yeah. So a royal flush is 4, and then straight flush will be, what is it, 16? Right, so because you can start at either, what is it, so you got to start at so you have to, you can start at jack, or at 10, or at 9, or at 8. So 4 per suit, right? And then
you can start all the way down to 2.
Yeah, well, I have 32 cards. So that changes everything. You got that changes both the numerator and denominator. So royal flush, then the probability of getting a royal flush when there are no two cards taken out yet. That's what you that's the chance. And you can certainly compute that number easily. The sort of another way to acquire those numbers is a Pascal triangle. So that one, remember this one? Adding up these numbers. So on the sides it's ones, and then I keep adding the numbers, two numbers above. Okay, so you can see those numbers that we have seen. Where are these numbers? 1, 4, 6, 4, 1. Remember where you come up? Right here. The number of, in how many ways I can choose 0 objects from 4, then in how many ways I can choose 1, 2, 3, and 4. And the numbers are how many? 1, 4, 6, 4, 1. Okay, so it is a row in my Pascal triangle. As I go to 5, I have 1, 5, 10, 10, 5, and 1. Okay, so that's in how many ways I could choose. I could choose a different number of objects out of 5. So this is out of 5, the last row. And so in the middle I have 2. When I'm choosing either 2 or 3, choosing 2 or 3 out of 5 will give me 10 possibilities. And that way you can continue on, and you can see the numbers are certainly increasing. And then 32, I'll have to make the 32 steps like this in order to reach, to be able to compute the, to use Pascal triangle to figure out the probability of the royal flush. Okay, so on and on. So that's Pascal triangle. Okay, so that's just another venue that we did not pursue. In this course, that we try to touch upon as many topics in mathematics as possible that you might be studying shortly. So we did algebra, and we did topology, and number theory. Okay, but this is what we didn't do. But that's certainly another possibility. I'm not sure the book, I don't think the book also has a lot of stuff about this. But this is a good place also to get started into higher mathematics. Okay, so what else I was going to talk about? So this is technically not set theory, so as long as set theory really does not limit itself to finite sets. It's just not, I guess, exciting enough. So these are combinations. What I was talking about and stop in the middle is how taking unions and intersections can be also done with infinitely many of them. Okay, that we did that in the when we talked about topology. So let's also do a little bit again. Say union of infinitely many subsets. Okay, so we did it. Remember this a union, and that's the notation. It's the difference. I want to emphasize the difference of notation. So A union B. Okay, it is like A plus B. Okay, but then there is another notation in addition. If you add many times in a row, what notation do you use? From calculus. I have to add n terms. What do I do? Sigma. Okay, so sigma, say a sub I. Okay, so sigma notation for series or finite or infinite sequences, and it works for both equally. Okay, so similarly, so like 1 from 1 to n, or sigma ai, I from 1 to infinity, also possible, or from negative infinity to infinity. So similar, we have a similar notation we have for the union, so we just draw a big U. Okay, so a sub I from 1 to n, or union a sub I from 1 to infinity. It's all possible. Okay, so first of all, what is it equal to? Well, well, the union is a union. So how do I write it? I'll just write it as all x in x, the universal set, such that x belongs to ai for some I. Okay? Similarly, and then you have intersection once again, so you draw a big intersection, you have a sub I from 1 to infinity, also possible. There's just one big upside down U. So x belongs to x belongs to ai, what?
Wouldn't it just be for some I from 1 to infinity?
No, I already have that. That's the union. The intersection?
That's what I was saying, for the union, whether it be one to infinity, not just for some I.
No, it is for some I. It belongs to one of those. It suffices to belong one of the sets on the list. If you do, then you're in. Intersection, what's the difference? In all of them, in other words, for any. So as you can see, that's the thing that commonly happens. For any there is replaced with for any. So the first line I could read as there is an I such that X belongs to AI. Okay, so you have a bunch of sets like this, and then all you need is one. So A sub I, there is an I such that my point X belongs to X sub I, A sub I. And on the other hand, so one is enough. On the other hand, I need to, for any one of them, I would have to, A has to belong to all of them. X has to belong to all of them in order for us to belong to the intersection. Okay, so that way, so if I want to belong to the intersection, I have to, X belongs to A sub I for every I. Okay, so, well, let me put it in the same order. There is an I. There is an I. X belongs to AI, or for any I, X belongs to AI. So we already saw the examples of this, but let me repeat it. So the union of, what is it? Say interval -1 minus 1 over n, 1 plus 1 over n, and from 1 to infinity. How about I make them closed? We had it open. What if it's there closed? What is it equal to? Remember this example? Do you know infinitely many intervals? What's happening to these intervals, remember?
Converging.
Well, the left end converges to what? -1, and the right one converges to 1, so that's the way to answer the question what the union is. So what is it? That it? Well, the essential, why I have to ask, because the endpoints. -1, 1 is the interval, but it could include it or not include it. This one is not inclusive, right? You will never reach 1 this way. So say 1 does not belong to any of these sets, so it's out. Every set, every point, no matter how close to 1, as long as it's less than 1, will belong to at least one of these sets. In fact, at some point it will belong to all of them. But the 1 is not so lucky, so it's out. And the other example that we saw, intersection of this, -1 over n, 1 over n. Once again, infinitely many. What's the answer? So remember, when you keep adding elements to a collection of sets, the union will grow. The intersection will shrink. So this will shrink more and more as you add more elements, as you progress through that sequence.
Actually, eventually be 0.
0, yeah. The only point that belongs to all of these intervals is 0. So the answer is 0. The point, I remember why it was brought up. It is what happens between when you do union of two closed sets is closed. However, when you have infinitely many, it's not closed necessarily. That's the first line. Okay, it might be open. And the intersection of two open sets is open, but when you take infinitely many, it's not necessarily. Okay, so that's the second line.
So neither one of those will really ever reach 0. So it's kind of like a space theorem type.
No, why do you say it's never, the first one, it contains 0?
Yeah, I'm talking about the second.
The last one, okay.
Like, as you go to infinity, -1 over n and 1 over n,
Yeah.
they go to 0, but they
Yeah.
never reach 0.
Right. No, but they contain 0, the interval. The points do not. It's just one point, another point. So if you just look at the sequences, that's the limit, so that's not it. Everything between those 2 points is contained. So because 0 belongs to negative 1n, 1n for every n. And this is, I can say, because 1 does not belong to negative 1 minus 1 over n, 1 plus 1 over n for every n once again. So, or suffice to say that there is an n. Suffice to say that there is, for some n, 1 does not belong to it, and that's it. So just example was the growth and growing and shrinking of sets, what you might end up with at the end. Yeah, so these are the unions, and then similarly, a similar idea that we had, remember the complements and how they interact with the units. So remember this one, A union B complement is a complement intersection B complement. So what happens if you replace finitely many the 2 and 3 and 4 finitely many sets? Will they still work? And the answer is yes. So once again, if I take the complement of the union A sub I, which could be of any nature, that's probably I should also just take a minute to talk about. So once again, De Morgan laws, remember, with infinitely many terms, and then in vice versa. The only thing that we have to worry about is what I want to make a next step to is we are used to sequences of sets. Hopefully this suggests of what we're talking about, but once again, the unions do not have to be countable. They could be uncountable too. So they don't have to be listed as a sequence. They could be just take any sequence of, take any collection of sets, elements of the power set. So you pick any collection of power sets, and then, so like this. So say alpha is a subset of px, and then you can speak of the union of alpha, and you can speak of intersection of alpha. Okay, so any collection of sets can be taken into the union. It can be taken in the intersection. If you look at that the definition at the top, it really does not matter whether or not there is any kind of actual numbers involved. So that's A sub I is really irrelevant. It's not important that we can actually attach a number to every element of the set. It's irrelevant, or we can attach, say, real numbers to those sets, and then everything works out as well. So just to mention, because at some point you run into this, is if you study topology set theory, or maybe advanced calculus, that also might come up. Elsewhere, usually everything is more finite. Okay, the Cartesian product also worth remembering. So we're doing algebra, or not algebra, but the set theory constructions with sets. And so we have union intersection of any number. We have complements, and we have functions, and we have a Cartesian product. So x and y are sets, and then the Cartesian product is the set of pairs. X cross y is xy, x and x, y and y. Okay, so once again, pure abstraction. X and y, there is no restriction on the nature of the sets. Finite, infinite, numbers, not numbers. It can be done. So if you see any kind of table with whatever data it is, so you have a list of you have something in the column, say spreadsheet, and you have here something, maybe names, okay, of employees, and then you have some kind of characteristics, or maybe I don't know, projects where's a meaningful idea of well, okay, how about, yes, employees and projects in some large corporation. Then forming these pairs, potential pairs. So you're pairing up a person with a project. Okay, you're certainly not going to assign every person to every project, but all the possibilities are open. So every pair, person, project is possible, and so that it will be the Cartesian product of what? Two sets. One set is the employees. The second set is the projects. The set of projects. Okay, and then so that you're not going to fill the full table. So you put a cross if you put the person on that project. Okay, so like this. So you're not going to fill the whole thing with crosses, but there will be multiple crosses in every row. There will be multiple crosses in every column. Okay, so in other words, you speak of a subset of the cross product, of the Cartesian product of these two sets. Okay, so that's how you can explain the idea. Certainly with numbers, that's explanation which outside of mathematics. That's what I did, if there is such thing. But certainly the real explanation is if you did take some mathematics, it's r cross r is r squared. So you take x-axis, y-axis, combine them together, you have the plane. Okay, you combine three. Certainly you can continue on in the same manner. We just talked about unions, intersections. You can go 2 and 3. You can combine, so instead of doubles, you have triples, and then you have quadruples. But then you have you can also allow infinite strings. So that would be infinite Cartesian product, which is also possible, but certainly not outside of mathematics. So, but this one is certainly to be remembered because it's very visual. And from real numbers and real numbers, you have your plane of all the real numbers. The why this was important in Calculus 1 because you did graphs. So graphs are subsets of the plane. So graphs of say y equal f of x is a subset of R2. Okay, with a certain extra restriction. So, well, we can say what that is. So it is equal to xy such that y is equal to f of x. This is the definition of the graph, and it turns out it is fully applicable to any function between any two sets, right like that. So all we know that it is a subset of x cross y, and so any function f from x to y, its graph is this. Okay, so that way we can. Of course, a bit silly because if you think about it, the whole idea of why we needed graph in Calculus 1, it is in order to visualize functions. And then we go to Calculus 2, 3, and then it kind of dies out a little bit because higher dimensions than 2, and the trouble to visualize there is the graph only makes things worse. So when we go to set theory, then graphs are a nice idea to connect back to Calculus 1, but really visualizing things is really hard because it's even more abstract than just high-dimensional Euclidean spaces, which is what creates the trouble in Calculus 3, so when you have to abandon all your abilities to visualize. Okay, so what else? Cartesian product. Well, one more thing is it also related to counting in probability and combinatorics is inclusion exclusion. I believe I brought it up. Counting the elements in a union. Let's say, that's fine. And then remember this. So x and y, they might intersect, right? So what's the size of the union? Let's say it's all finite, so we don't have to worry about it. How many elements in the union of x and y? The number of elements in x plus the number of elements of y and minus the number of elements in the intersection, right? Okay, so that is the inclusion-exclusion principle when you have only two. But once again, we know that we can have any number of elements in the union. So I could, if I go with 3 now, that's a bit tricky. X and y. Naturally, you start here, and then well, if I make a picture, you'll see that I do not. It is natural to assume that you just subtract the triple intersection, but that's simply not the case. So if I have 3 x, y, z, okay, so we need to make sure that we don't double count everything. So right now I counted everything, but the ones, look at it, I counted some pieces, I counted twice, and some, in fact, I counted 3 times. Okay, so these I counted at least twice, these, right? The intersections are counted twice unless it's a triple intersection which is counted 3 times. So what do? And this is the trick. You subtract the pairwise intersections. So x intersection y minus x y intersection z minus z intersection x. I subtract it. Now you see what the problem is. I subtracted the sizes of the pairwise intersections. So I subtracted these. You see the problem?
You need to add the triple intersection?
Say it again.
You need to add the triple intersection?
That's right, yes. Because I subtracted too much. Because I subtracted this one, well, I subtracted it 3 times. So I have to add the triple intersection, right? So x intersection u, y, z. So then the idea is the pattern that appears. If you have n elements union, then you have to go through this from single sets to double intersection to triple intersection and carry out this computation on and on. Except the interesting thing, it will alternate the signs, plus minus every time you make up the difference. Okay, so we have a few minutes left. Let's do one more. Proof by induction. I have it somewhere in formula. Yeah, this one. I'm not sure. I don't think we saw this. So 1 squared plus 2 squared plus 3 squared plus n squared is equal to n plus 1, 2n plus 1 over 6. Step 1, what's step 1? Base, okay. Base, you can choose any one that is reasonable. It doesn't make any sense, any difference whatsoever. The small the better. Even though there is a remote chance that it's too small, and then you might trick yourself into thinking maybe it's not true in the first place. But it appears that n equal to 1 should work. So we have 1 squared on the left, and on the right have 1 times 2 times 2 times 1 plus 1 over 6. It is equal to 1. Okay, works out, checks out. So we're fine with the base. Step 2 is to formulate, just in case, write the inductive hypothesis, which is exactly the same as the statement that we have to prove. So I'm not going to repeat it. But that is, remember the way we wrote it, it's like P sub Pn or P of n. So it is the assumption that the formula is holds as is for some n, for a given value of n, for any value, not for any value n. We assume that it is true for n. So true for n. Step 3, derive Pn plus 1 from Pn. Okay, so we start with, we have to write Pn plus 1 and work our way down, or conversely start with Pn and then try to add things to it. Doesn't matter. It's just the way to discover the proof, but then if you discover the proof, then writing it up in any manner that you prefer is not as much a challenge as to finding it. So Pn plus 1, what is it? It is 1 plus squared plus 2 squared plus n squared plus n plus 1 squared is equal to what? N plus 1, n plus 2, and here 2n plus 3? Yeah, still over 6. Okay, so the good news is this, right? So we are able to get rid of the dot 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 business. That's the difficult part in this kind of problem. So you have not infinitely many terms, but you don't know what's happening in between whether you're doing it just for like a finite sum, or it is typically when you deal in calculus, it's a series. You're doing series, and then there is dot 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 there, but that's it's not helpful. Even though you can compute it for every n, if you want an explicit formula, that's you want to do this what we're about to do. Convert it into a compact formula. It's like a computational, computing things with a computer, or computing it by a single formula. So consecutive, like a spreadsheet, you're spreading out down line by line, adding an extra term. That's the left-hand side. Works out as long as you are prepared to go. Or you just you plug in, you just plug in n into the formula on the right, and that's it. So you don't have to go through this long computation. So, okay, we know what this is by, this is equal to, well, whatever it is we applying, it's better to apply the hypothesis as early as possible, and the simplification will be ours right away. So we have n plus 1, I'm reading off the original statement, over 6, plus n plus 1 squared, is equal to whatever, well, equal to this, right? So I don't have to rewrite this, equal to this. Okay, so that is the simplification that we were after, and we now have it. And so all we need is to prove this, and that is usually should be straightforward. It is pure simplification, right? So there is really no challenge in that matter. So it's pure algebra. You have to simplify it to a degree that left hand side is equal to right hand side. So let me just carry out this multiplication. So I'll have 2n plus n squared. N squared plus n. So I can only do one at a time, so sorry about that. 6 n squared plus 2n plus 1. Okay, so little by little I'm just expanding it. And here I have n plus 1 times n plus 2. What does it give me? N squared plus 3n, I believe, plus 2. Okay, just expand, put 6 out, pulled 6 out. And now I'm expanding a little by little, and then in hopes that everything will cancel out, and I do believe it will. So okay, let's try it. So I have 2n squared plus 2n cubed, 2n squared, 2n cubed, 2n squared plus n squared plus n. Okay, so that's the first term. Over here I have 6n squared plus 12n plus 6. That's the second term. The right-hand side is long, so there are going to be 6 terms. So I'll have 2n squared cubed, 2n cubed, plus 6n squared plus 4n, I believe. Yeah, just if you see I make a mistake, just stop me. Plus 3n squared plus 9n plus 6. Okay. Let's start canceling. 6. So starting from the bottom, lowest terms. So terms with no n, these 2 6s and nothing else. So that works out already. So now let's progress to terms that have n contain n and nothing else. So these are the ones. Okay? 13 and 13. Okay, so they're gone too. So now squares, this is a square, that is a square, and all of these are squares. So I have 3, one more. 3, so it's 9 on the left and 9 on the right. Okay, so it's gone. And finally we're left with only one term left. That is the cubic, and their 2n cube also match. So there's a match. Everything cancels out. 0 is equal to 0. I did not write it up, but if this is, as a written text, this is unacceptable because it's just a computation. You have to explain what has happened. You have to say that, like words, what would you, how would you explain it? So I arrived at 0 equal to 0, that which of itself, you started with a statement. You went through logical steps, and then you say, well, and they going from left to right, and then the conclusion is 0 is equal to 0. What does it prove? Starting with statement A, then B and C, you following your logic, and then you arrive to a conclusion 0 equal to 0.
So thus, Bn equals Bn plus 1.
No, I intentionally took us out of the context so that we could look at it in a broader sense. So once again, you start with a statement A, okay, and then you draw a conclusion from A, which was B, and then from B you derive C, and so on. And at the end of this computation of this derivation, and per every statement is perfectly correct, at the end you end up with 0 equal to 0. What does it prove?
It's true.
Anybody wants to correct this? So forget about the context again. Look at the abstract. Is 0 equal to 0? So you arrive to a conclusion that you knew all along. So what is the point? How you can conclude that anything about anything if you arrive to a conclusion that is known to be correct? So it means nothing. If you arrive to 0 equal to 1, that proves something. What does it prove? What?
Prove that 0 and 1 is the same, or
Say it again. From A, I derive through a sequence of computations, I arrive to 0 equal to 1. What's the conclusion?
assuming that all the statements are correct.
Yes.
Be that 0 equals 1.
No.
Not sure.
No, it proves that A is wrong. That's the proof by contradiction. You start with the statement A, and then you arrive to a statement which is known to be wrong that proves that A is wrong. Okay, that's proof by contradiction. What is about the previous line? What is the previous line? It is a logical fallacy.
Yeah, because we assume all cases are true just because we found one case that's true.
We are well. The thing is that if you start, that's where a flaw comes from. Why is it this a flaw? To conclude anything about A, such as A is true, is wrong, because you can start with a wrong statement, go through perfectly correct logical steps, and arrive to a correct statement. I mean, it's not really that hard. Well, let's do it once. 0 is equal to 1. Which follows 1 is equal to 0. Right? And now what I'm going to do, I'm going to add these two together. I add these together. What's the conclusion? 1 is equal to 1. Okay. You see, the problem here is I started with the wrong statement. I arrived to a correct statement. So, which means that when I arrive to a correct statement, it means nothing. So how do we? So that's good thing that even on the last day of classes, it happens at least. It did happen. Okay, so okay, so I hope you see this and remember this forever. So how do we fix it? We have only 2 minutes to fix this. How do we fix it? I mean, our proof. How do we fix our proof of the inductive proof?
Is the whole proof wrong, or?
No, we can
Just
fix
the
it.
last
We can
one.
fix it. There are no words. That's a point I started to make. Is there are no words, and so if we just assign write words to describe this computation, we'll be fine. It is illogical. So how do we fix? Let's take a look at that line again and ask ourselves how do we fix? What what is missing. What should I change in the sequence of conclusions in order to be able to make the conclusion that I want to make? The conclusion that I want to make is A is correct. There is something missing. To make it correct, to conclude that it is correct, what do I need? What do I miss? In the sequence of conclusions. Well, this. So if your transitions are equivalence transition, going backwards, and you arrive to a correct statement, then you have proven that A is correct, because you have demonstrated that A is equivalent to 0 equal to 0, right? Which is good. So it is. So your statement is as true as 0 equal to 0. Okay? So it can be done if your transitions are equivalences. And that is the comment that is missing here. So these are equivalent. So once you carried out this computation, you can accompany this computation with that comment that each of these three equations, 4 in fact, 1, 2, 3, 4, are all equivalent to each other, which means that the initial statement we started with over here is also correct, just as correct as the last one. Okay, well, and then which is actually a less important conclusion, I suppose, or lesson than the one that you do not draw any conclusions from a sequence of implications like that. So if it is one directional implications, you cannot draw any conclusions by arriving to a correct statement. Arriving to a wrong statement tells you something, otherwise nothing. So that is probably a very good thing to remember. What can happen? Wrong statements, correct logic brings you to a correct statement possible. Okay. All right. So we'll just stop here.